almost an embarrassing introduction, but I'll try to get past that. And with Sarah, I guess the thing I'm most disappointed about is that I can't be there and meet the students. But I remember the Cage Brewing. Is that what it was called? That was last time I was down there. That was the
That's
place.
right. Yep.
Yeah, and I wish we can go there. Although we're having very much a Florida-like day here in New Hampshire. It's going to approach 90 degrees. Let me share my screen and tell me if that works, and we can get started. Is that working? Yeah. Okay.
Yep.
All right. I'm going to go right to the next slide, actually. And Steve mentioned our center up here, the Center for Coastal and Ocean Mapping. It's NOAA part called the Joint Hydrographic Center. I show a nice picture down below of our seaside facility. And of course, that's in the summer. I don't think I'd want to show you a picture of what it looked like in the winter. But as Steve mentioned, we've been around kind of since 2000 or so, and we're just delighted to see the evolution of the Center for Ocean Mapping and Innovative Technologies at USF. We've already been working closely. For years, I've worked closely with you guys, but now our whole team is working closely with you guys, and I think together we're really hopefully we'll be doing great things for ocean mapping and ocean science in general. For NOAA and for the nation. I'm really looking forward to that collaboration, and clearly the NOAA and the government has put a lot of money into this concept of ocean mapping, and both here and now at USF. And if we ask the question why. Originally, certainly in our case, the focus was that part of NOAA that was looking at safety and navigation, and the folks who have to make the charts, the Office of Coast Survey. And that, of course, has been a great focus of our efforts. It'll be a focus of some of your efforts, too. But I think what's happened over the years is that as our capabilities have improved so much, it's been recognized just how valuable seafloor mapping data can be for many, many different applications. Habitat and ecosystem mapping, an area that you guys are certainly excelling in. We need to understand the distribution of depth so we know how deep currents flow and distribute heat, but also how we understand the effect of topography on turbulence, which is critical for climate models. We have to worry about natural hazards, landslides, gas seeps, and so on. Have to survey for cables and pipelines. Of course, we need to understand what the bathymetry looks like to understand tsunami inundation, storm surge inundation. Much of what we understand about Earth processes, particularly plate tectonics, came from geophysical surveys, bathymetric surveys. There are, of course, national security applications, marine heritage. There are hundreds of thousands of wrecks preserving a history of mankind, literally scattered around the seafloor. And the one that I most truly love, all the things we don't know. What are we going to find when we go out and map the pure exploration aspects of it? So there's lots of good reason, and we're both grateful that NOAA has recognized that, and the nation has recognized that, because this has really been formalized. The recognition really over the last few years that we can't manage, we can't sustain, we can't protect what we don't know and what we don't understand. And so fundamental understanding of ocean processes, fundamental to the understanding of ocean processes, is the establishment of what I call the geospatial framework. And we see that this has been formalized through White House summits on ocean science and technology, which had a strong focus on ocean mapping that led to a national strategy for mapping, exploring, and characterizing the USEEZ, and that strategy now even has an implementation plan. So you see there really is a tremendous national focus for this. And again, it's this recognition of the key to this geospatial context. And we're very fortunate because modern remote sensing techniques have allowed us to establish this geospatial context with extraordinary precision for almost anywhere on Earth. Remote sensing techniques can let us view the planet in I said, tremendous detail and look at processes. We can look at geomorphologic and tectonic processes. We can look at cryospheric processes. We can generate very, very high precision digital terrain models. And we can even extend that even further than just heights. We can start looking at thematic information and look at land cover types and the health of forests. It's really what's remarkable what we can do um, from remote sensing. And while originally this was very hard to do, I think all of you know that any 5-year-old can now just, with a few swipes of a button, zoom into almost anywhere on Earth and look at it with tremendous detail. And this is really, really a huge revolution in our ability to understand Earth processes. The problem is, this is really only true for the brown and the green, and in this case, gray parts of the Earth. What happens if we use those same sensors and we point them to the blue part of the Earth? Well, if we go and zoom in there, all we're really going to see is this. And we, of course, know why. It's because the electromagnetic waves that we use to image through our remote sensing techniques, the land, just do not penetrate into the ocean. And in a coastal ocean where it's more turbid, maybe 50 meters. In the deep ocean, light will penetrate maybe 200 meters. And so we just can't use those same techniques. We can't generate a Google Earth for the ocean very, very easily. We've taken a look at what it would take to do that. I was actually asked by Google to sit down and figure out what would it take to make a Google Earth equivalent at the kind of resolution that Google Earth has. And we understand those limitations, how far light can penetrate. We're fortunate that we've developed technologies that now let us penetrate through that impenetratable water. We can bring remotely controlled vehicles down close to the bottom because light will only propagate so far. So get within 10 meters or so of the bottom so we can image. We understand how far that light will travel, what we cover in a typical image. And if we think about that and do a rough back of the envelope calculation, to cover the seafloor, we'd need about that many images. In other words, that number, 600 trillion images or so. And we can argue about how long it would take to do that. Takes time to get a vehicle down. The vehicles don't move very fast once they're down there. Oh, I might be off orders of magnitude, but the bottom line is to collect 600 trillion images. It would take hundreds of millions of years. And so we're really not gonna, in our lifetime, even the student's lifetime, we're not gonna be able to generate the electromagnetic equivalent of Google Earth. And so we have to look for different ways to penetrate that opaque cover of the oceans. And we've been doing that for thousands of years, literally. People have tried hard to measure the depths. If you look at this statue from an Egyptian tomb from 2000 BC, we see the Egyptian ocean mapper sitting there up front with his lead line to throw out to measure how deep it is. I'm going to track in these slides the density of data that comes from the technique. So we get this in terms of megabytes per hour, some tiny small fraction of a megabyte an hour with Egyptian lead line. If we jump ahead something like 3,500 years or so and take a look at the next picture I was able to find, a wood carving from the Thames River, we see the technique hasn't changed one bit. They're still using a lead line. 3,500 years later. But if I jump ahead now 500 years and we look at, say, 1940 or so, what do I see? But basically the same technique. So for 4,000 years, we've really only had one technique, a hunk of lead at the end of a rope to measure the depth of the ocean. And that was really until the echo sounder was developed, the recognition that we can't use electromagnetic waves. Hanging a piece of lead at the end of a rope is inaccurate, time-consuming. That's really not going to be a way to do it. But we can take advantage of acoustic waves, which, unlike electromagnetic waves, travel very nicely in seawater. And this was really promoted or prompted by the sinking of the Titanic. So in between the First and Second World War, a lot of effort was focused on trying to develop echo sounders to look ahead and see icebergs. And somebody realized you can turn that downwards and start measuring the depth of the ocean. And so kind of perfected during the Second World War, coming out at the end of the Second World War, the concept of what we call single beam echo sounders was developed, where we now can send out an acoustic ping and wait for its return when it counters a material with a different acoustic impedance. If we know the speed of sound in the medium, seawater in this case, which we do, we can time that and get an estimate of depth much more rapidly, obviously, and more accurately than with something like a lead line. And we see that first quantum leap in terms of megabytes per hour in terms of data. Now I'm going to stop here for a second, and this is a slide I've been using for many years, and for many years I gave credit to one of our early students, Rick Brennan, who created that animation. And I know many of you know Rick in terms of his work in setting up COMIT, and I suspect many of you know that tragically Rick passed away a week or two ago, and it really was a tremendous shock to us and a tremendous blow to us. He was really much more than just one of our first students. He grew to be a friend, a colleague, a confidant, and most importantly, like many of the best students, he turned around the mentor-mentee relationship, and he became our mentor in many different ways. Now, the only consolation I have in the loss of Rick is that I know the great number of contributions that he's made over the years. He's really been a tremendous contributor to NOAA, to OCS, to NOAA, and to the nation. And we're very grateful for all he has contributed, but it is going to be with everlasting sorrow that we think about how much more he could have contributed. And I hope you'll all join me in thinking about him some and thinking about how much he'll be missed and all that could have been done in the future. It's really a sad note, and I thank Rick for I thank Steve for letting me say a word about our friend and colleague. Okay, so we have the single beam echo sounder that was developed. One of the things about the single beam echo sounder is that as the sound leaves the transducer, it spreads, and it spreads laterally, much like if you took a flashlight and shine it in a distance, the light beam spreads. And so by time it reaches the seafloor, it's insonifying something like half the depth all at one time, and there is no angular discrimination at all in that cone of sound. And so we get one return back from it. That return is going to be from the shoalest feature in there. So if we had a shallow feature off on the side, we'd get that depth reading, but it's the only thing we know about its position. The only thing we can assume is that it's directly below the ship. And so with the single beam echo sounder, we're looking at this kind of very broad, laterally interpolated picture of what seafloor depths look like. It's a very smoothed out version of it, and we typically look at it in this two-dimensional picture. And so over the years, as people went out and collected single beam echo sounder data, you see here coming out of Scripps, where I did my graduate work, all the ships coming out, each with their single beam echo sounders, we'd get that kind of blurry single track. And then usually a human interpreter, and then now computers can do it too, would kind of put together the dots and create contours. And in the late 1990s, this was our very best depiction of what the bathymetry off the Southern California coast looked like. And so this was really in the late 80s, the state of the art. There was something else very important going on, though, at that time, and that was the development at Lamont built with Walter Smith and Dave Sandwell of deriving bathymetry from satellite altimetry. And I think you've all seen these remarkable maps of bathymetry generated by the fact that large features on the seafloor, like seamounts, will affect the gravitational attraction, will affect the geoid of the Earth, actually. And so the vectors, the gravity vectors, will converge towards a large feature and actually push up the sea surface. If you have an absence of mass, like a deep trench, the vectors will go in a different way and you'll depress the sea surface. And so by having very accurate satellite altimetry measures of sea surface, you can get an estimate of what the bathymetry looks like, but it's at a very coarse scale. It's interpolated at about 2 kilometer spacing. The actual resolution is a little less than that, but from a tectonic process scale, in terms of the distribution of trenches and ridges, it's a phenomenal picture of the Earth and has really revolutionized our ability to look at tectonic processes and help us zoom in on places where we want to take a closer look. But if we're really going to address all those issues that I showed in that Y slide, all those process-based issues, satellite altimetry just won't do. And I tried to demonstrate this. I was gave a talk in Monaco. The Prince of Monaco was there, so to demonstrate that, I had to show him what his country looked like with high resolution imagery. It's not a problem there. You can see everything beautifully. We can generate from satellites digital terrain models at relatively high resolution. This is not such a high resolution one, maybe 30 meters. And if I show that, you can certainly still pick out all the features. But if I now take this imagery and I degrade it down to the resolution of our satellite-derived bathymetry, that becomes something like that. And I had to apologize to the prince that his country disappeared. And that's the scale at which we're looking at that satellite altimetry. When we look at global maps of it, it looks fine. But if you zoom in, and here I'll just zoom into a 200 by 200 meter piece of seafloor, we're really looking at something that looks like this. And the addition of single beam bathymetry, all the single beam bathymetry tracks that we have, doesn't really help this, because at the end of the day, with an average ocean depth of 4,000 meters, the single beam bathymetry has a resolution of about 2 kilometers too. And so this is really the picture that we have for a good part of the ocean. Actually, it's all we had for the ocean until, again, it really started in the late 70s, but perfected and coming out of the military in the 80s and beginning of the 90s. A new technology came along, and that was multibeam sonar. And with the multibeam sonar, a technique is borrowed from the radar community, beamforming technique, and something that the radar folks developed, where we have orthogonal arrays. We have an array that is long in the along-ship direction, and that creates a transmit pulse that's very narrow in the along-ship direction. The ship is moving in this direction here, and very wide across the track. So we transmit a beam that looks something like that. This geometry is called a Mills cross or a Mills T, again named after a radar scientist. But at the same time, what we do is receive on an array that is orthogonal to it. It's elongated in the across-ship direction, and that receive array is formed into a number of individual beams. It could be hundreds of them across track. And at the end of the day, we mix the transmit in the narrow beam across track with the receive beams that are narrow in the along track direction, and narrow in the across track direction. We get the cross product of the two. And so at the end of the day, we end up getting soundings from each of these little narrow beams on the seafloor. And again, there can be hundreds of them simultaneously, each one with very high lateral resolution, and these systems have tremendous vertical resolution. So suddenly that big, broad picture we had of the seafloor is now a bunch of discrete individual soundings. We've gone from a situation like that with the single beam to now hundreds of individual soundings across a wide track. And if we look now at our data density, we went up with the single beam, and then with the multi-beam, we've just shot up tremendously. These systems ping faster and faster as we get in shallow water. And with some of our shallow water systems, we're easily generating a gigabyte of data an hour of bathymetry. And when I start talking about the water column information, we can be talking about a gigabyte of data a minute. So we've really changed the world of data density. We've changed the resolution we got. And with the concomitant advances in things like navigation, motion sensors, because we have to worry about how the system is moving on a vessel, with computing advances and visualization advances, we've truly revolutionized the way we can look at the seafloor. And I like to go back to that 200-meter patch of seafloor that we looked at before. That's an area off the north of Hawaii. That's all we had up until the first multi-beam pass of it. And when we run the multi-beam through, we change that kind of depiction to this kind of depiction. As it says here, what a difference a swath makes. Now we're looking at something at a resolution that we really can start looking at processes. We can see a flat top here, which implies sea level interaction of some sort, we can start seeing downslope processes, all kinds of things that we need to understand the Earth and all those other Y issues that we talked about. So that's the kind of depiction we need of the seafloor if we're really going to carry out our mandate of NOMIC and a global version of that in terms of mapping, exploring, and characterizing the seafloor. And so applying that technology, Jim Gardner and I, Jim, who was at the USGS in charge of the West Coast Mapping Program, we spent a couple of months when multibeams first came out off Southern California, and we can turn a map that looks like that, which again, the best depiction in the, actually up until the late 90s, to a map that looks like this. And as you can see, this new perspective offers a remarkable new set of insights into, again, downslope processes. And again, we've compromised on resolution. We have high resolution data up here too. It's just hard to show it all at once, but canyon forming processes and so on. And so again, we've stepped into a whole new world that really lets us address many, many new applications in terms of ocean mapping. But that's not all, as the commercial says. Along with the depth information from these sensors also comes backscatter information, the amplitude of the return. And so we can take a picture like this off Oahu, where we're looking at the bathymetry from about 40 to 800 meters. We see a bunch of beautiful sediment transport features. This is a big current whipping around Hawaii here. But we went out there because there had been dumping out here for years from an old hospital that was built in Hawaii. It was dismantled, dumped out here. They were wondering what the impact of the dumping was. And there's no indication at all in the bathymetry of this dumped material. But if we add this new degree of freedom, this backscatter information to that picture, what we see is something like this. And now we're getting a response of the seafloor material, either its roughness or its hardness. And all of a sudden we can see this area here where there had been a tremendous amount of dumping, the material smoothed out by this current, but we can also see each individual here in 600, 700, 800 meters of water. This is when a barge goes out, opens up its hoppers, and you can see each individual barge, what it dumped. And there was another type of dumping there where there was a conveyor belt, and you can see cases where you see the conveyor belt dumping material too. So it opens up a whole new dimension going from where the bottom is to what the bottom is, which has been used tremendously. It's been very, very valuable in terms of locating hard grounds associated with seep communities, where the backscatter is very indicative of those areas. And we in our lab have been trying for years to be much, much more quantitative about this, really trying to use the physics behind what creates the backscatter, looking at what we call the angular dependence, the fact that we have a reasonable theory for how backscatter should change as a function of angle, and be able to extract that angular dependence of the backscatter, put it into an inversion model, come out with a bunch of features, we call them, that represent the inverted curve, and then through a bunch of smoke and mirrors, come up with a guess. And all it is really a guess, but hopefully an educated guess of what the material type will be. So that's one really powerful potential approach to actual seafloor characterization in terms of the angular dependence. But we also know there's another strong dependence of the bottom return, and we've been more recently focusing on that, and that's the frequency dependence of the seafloor. And so we've been looking quite a bit at how seafloor responds at different frequencies. In this case, again, a brute force message using different vessels with different multi-beam sonars on them, creating, in essence, an RGB type plot for response to frequency that is apparently helping sort out different bottom types, but even more excitingly now developing tools that let us all at once, in this case, look at 70, 120, 200, and 330 kilohertz, and in a single experiment, measure the seafloor at a range of angles and at a range of frequencies. So we can build up this three-dimensional frequency versus angle curve, which should be the most characteristic aspect of the seafloor type. And so we're trying to now go into this new dimension of characterization, not just where the seafloor is, but what it is. But again, as the commercials say, there's still more. And that's that the sonars in the last 10 years or so have given us more than just a seafloor backscatter. they're also giving us the water column backscatter. And we've now got the computing capability to record that. We're developing tools to visualize that. It was first developed to look at fish and look at the behavior of schools and maybe even try to be more quantitative about it. But we quickly, and we're kind of thrown into the deep end, so to speak, with Deepwater Horizon, as Steve is so familiar with, and we were working very closely with Steve at that time. Just a few months before Deepwater Horizon, we were coming in on the first deepwater multibeam that had water column mapping capability, the Okeanos Explorer. And as we were steaming into San Francisco, going over this feature here, what did we see but this amazing target, which clearly to us was a gas seep of some type. It wasn't surprising. It was an area of known gas province, but it just was amazing to us how sensitive that multibeam was to those small bubbles in the water column. And so we quickly focused on developing visualization techniques. In this case, we had to go right back to port, but we came out a few weeks later to see if this was still there. Was it an ephemeral feature or not? And sure enough, not only was it there, but we were able to map a whole series of these along a strike, along a fault. And so, again, it wasn't surprising in terms of the area, but we were just really impressed with how sensitive that multibeam was to allow us to do that. And just a few months after that, Deepwater Horizon happened. And so when we were asked to come in and try to find the deep plume and eventually to look at how well the well was capped, this was the technology we tried to bring in. And amazingly, and this was probably one of the most sleepless weeks of my life, when the well was finally capped, there was great concern that there'd be a sidewall breakout. I was on the Secretary of Energy's review panel. I got a call from the secretary saying they're worried there's going to be a breakout. Can you guarantee, that's a very dangerous word to a scientist, guarantee that if we cap the well and it is leaking, you will be able to see gas leaking from it. And so I kind of thought we could, and I checked with all my smart acoustic colleagues here, and we came back and we said, yes, we were confident we could see even a small leak if it was occurring. And so over the objection of BP, as it always was, the secretary basically sent our vessel over the wellhead. We had never been allowed over the wellhead before. And this is after it was capped. And this is what we saw. We saw a gas plume coming out. And so this tripped a whole procedure. BP had to send a bunch of ROVs down right away. And what they found was that. It was a tiny little leak on one of the flanges on the cap. It was nothing serious. This is hydrate, oil-stained hydrate here, but there's just a few bubbles a second coming out, and that's all it was. And they kept their ROVs on that the entire time till the well was cemented in, making sure it didn't get any worse. But it just showed how sensitive a tool the acoustics can be. That little leak created a target that looked like that. And so again, I think it really opened our eyes to what a powerful tool the acoustics were for characterizing now gas in the water column, both natural leaks and natural seeps and man-made leaks. And this has now become a very, very powerful tool in the oil and gas industry for exploration and also for hazard investigation. And so there's been lots and lots of work now following up on trying to quantify. It's also affecting our view of how much methane goes into the water column. And I think it was something that was not accounted for in many of the climate models. And so we're trying to push that even further. Our early work really focused on finding them, locating them quite precisely, but now going to the use of broadband sonars, we're focusing now on measuring the flux of gas. And we can actually identify individual bubbles with a broadband sonar. If we can measure an individual bubble, we have a theoretical basis for bubble size versus target strength. If we have a calibrated sonar, we can get the bubble size from the target strength, we get the rise rate, and we can measure flux. And where we've ground truthed this with ROV measurements, these flux measurements have not been far out of whack. But again, there's still more in the water column, and this has been probably the most exciting things we've begun to see. We've known for quite a while that when we have a major impedance contrast in the water column, when you have fresh and salt water mixing, we can occasionally see that with a high frequency multibeam. Here we have a case of actually seeing an internal wave breaking. This is in an estuary, and here a Helmholtz wave. And so this we've been, we're learning how to better tune the multibeams to do this, but we've known about that. What really surprised us is our ability to see very, very subtle physical oceanography. And here from some work we did on the icebreaker Healy, way high up in the Canada Basin in the high Arctic. We were steaming along with our 12 kilohertz multibeam. We were at a station here, actually, a CTD station. You can see the CTD going down in the multibeam, coming back, lots of fish. The bottom, the strong red return is the bottom from the multibeam. And, we've always seen lots of noise near the hull kind of up there, and we just kind of ignored it until one day I took a little closer look at the CTD. And when I zoomed in, I noticed that this band here, and look at this change in the CTD. And I said, that can't be a coincidence. And then these little funny steps in the CTD. And so what we did is broke out some much broader band, some fishery sonars that we had, which are broader band, higher resolution. And we took a look at this area in the water column. And what did we see? It was really quite remarkable. We saw hundreds of thermohaline steps, and these are a well-known phenomena when you have cold fresh water over warmer, more saline water. You get double diffusion. The heat diffuses at a different rate than the salinity, and you get these. This is a CTD profile. You get these tiny little steps, sometimes little larger steps, going along kind of 30, 40, 50 centimeters apart, a meter apart or so. And we were able with the sonar to discriminate every single one of them. Here's a zoom of them. Here you look at each step here, and these are the reflection coefficients derived acoustically and then measured from the actual properties of the water column. So it was just an eye-opener to us again about the amazing resolution that we can get in seeing oceanographic structure. And so we pressed this and watched thermohaline steps fall apart and start seeing turbulence. In another area, we were able to, without thermohaline steps, we were able to track the mixed layer, the thermocline, for hundreds of kilometers and watching its behavior. And in this case, we're not fully sure what we're seeing here, but we think we're seeing an internal wave that's broken and entraining air. So again, this has now raised the level of what we can see to a new height. And most recently, Liz Widener, one of our graduate students working in the Baltic, has been able to use this approach and literally map the anoxic layer. It's not the anoxic layer that's being mapped. It's association with the salinity change with the halocline, but it's just a perfect correlation between the oxygen minimum and the acoustic target. And we now, through the Baltic, can map that over large ranges. And so we're mapping the dynamics of the oxygen minimum layer in a way we've never been able to go before. And so we've made a lot of progress since that first multibeam. And if I just want to take a second to look ahead, where I think we're going to be going, we're going to see increased bandwidth in the multibeams themselves. I assume I'm pretty sure we'll start seeing chirp multibeams. Got to beat all you can out of the transducers in terms of getting that resolution that we can use from the broad bandwidth. We're seeing lots of effort to calibrate the multibeam system so that backscatter is not a relative measure, but an absolute measure. We're seeing lots of approaches to increase the data density. We're seeing multiple solutions per beam in terms of both backscatter and bathymetry. And why be constrained with that fan-shaped beam? Why not be able to? And we think we can generate an annulus. And so you have multiple annuli. So every time the sonar pings, it's putting out a ring and maybe a growing ring. And so we'll be able to instantaneously look at the seafloor at multiple angles in multiple directions all at once. We're seeing lots of the software move to the sonar itself, better integration with sound speed, better estimates of uncertainty, and lots of automatic processing tools, and we'll come back to that. And the one big leap, and I'm not sure I'll have time to talk about that, but we may have a way to start taking advantage of sparse array design and having a huge array, having a 40-kilometer array out on the seafloor that'll give us meter level resolution in 4,000 meters of of water. It won't increase the rate at which we can map, but it certainly could increase the resolution. And if we have time, we can talk about that. But all of these are constrained by the physics, the trade-offs between resolution, frequency, propagation range. We're not going to change that. And so if we're really going to make a big advance in terms of our ability to cover lots of area, we need to think about the delivery systems, how we deliver these sonars, these physics-constrained sonars. And so a lot of the effort in our lab has also now been looking at autonomous systems as a force multiplier. How can we use these to increase the footprint, in essence, from a mothership and maybe a bunch of little ducklings? We work with some little ones to develop software, a 4-meter vessel that we've been working with for years. Now, again, used to be our workhorse. Now it's becoming the development platform for software, and a new vessel that we're going to take delivery on it. We've been playing with a loaner, and now we're going to take delivery on one in July of a 7-meter purpose-built vessel that's wave piercing. And the idea is, again, that if these vessels can survey as this one can at 10, 12 knots, keep up with the mothership, we can have a real force multiplier. And instead of a single ship being constrained by its coverage, we can now multiply that by 2, 3, 4, as many of these as we can operate at the same time, and really start enhancing the coverage. And so we've come a very long way. This is the map that Matthew Murray Fontaine created with 80 soundings in the Atlantic. And we've gone from, let me go back to that picture of what the Atlantic bathymetry looked like to a picture that looks like this. But for the most part, that picture is still based on that satellite altimetry, and so, or single beam sounding. So if we look at it from this distance, it looks great. But as we zoom in, we really lose that resolution that we need to look at processes and all the applications I talked about earlier. And so I ask the question now, how much of the seafloor is covered by modern multi-beam data? And if we go into the National Center for Environmental Information, the old NGDC, who is probably the largest repository of global multi-beam and all bathymetric information, and plot their data holdings, it looks something like that. And wherever you see blue, there isn't, where it's all the greens and the yellows and the oranges that are the coverage. And you see some areas look pretty good, others not so good. But if we even take a look at a place like this, which looks like it's got great coverage, and now zoom in on that, what we see is that it is not great coverage because, again, we're trying to show the entire world, and a swath in the deep ocean is maybe 20 kilometers wide. So at this scale, these swaths are way, way larger than 20 kilometers. And so even there, most of it is uncovered. So we built a new tool. We call it BathyGlobe, which lets you zoom in anywhere on the world, and then at true resolution, see what's covered and not covered. So just pick an area here. It'll pick up an 1,100 kilometer by 1,800 kilometer area. Wherever it's yellow is modern multi-beam. White is really old multi-beam, not so well navigated. And the little tiny white lines are single beam data. So this is the area where the MH70 airplane crashed. And when they went to search for it with autonomous underwater vehicles, it turns out they were off by 1,000 meters in terms of the estimates of depth. And you could see why. This is the only data in 1,100 by 1,800 kilometers. That's the only data they had. And the rest was all broadly interpolated. And so now actually there's much better coverage there because they've Fugro has provided that data to the database. So if we look, and I'm going to step back a couple of years because I now want to talk about Seabed 2030. So if we look at the status at the first look of the Seabed 2030 program of what the coverage was, it turned out that in 2017, 2018, about 6.9% of the global ocean was covered with available, and I emphasize available. There may be more collected, but if it's not available, it's not useful, with available multi-beam data. And this was recognized by a bunch of us as a real problem. You know, if we are going to be serious about understanding this planet, we need to have that geospatial context. And a fellow named Yoi Sasakawa, who's the chairman of the Nippon Foundation, which is a huge philanthropic organization that focuses on maritime aspects, in 2016 in Monaco at what we call the Forum for the Future of Ocean Floor Mapping, basically challenged the community to see if the global ocean could be mapped seafloor by 2030. And a group of us responded with a proposal. And in 2017, Mr. Sasakawa at the UN's Ocean Conference announced the start of the Nippon Foundation-GEBCO Seabed 2030 project. So this is a collaborative project between the Nippon Foundation and GEBCO, the organization in Monaco that's responsible for deep sea charts. And its goal is to inspire the complete mapping of the world's ocean by 2030 and to compile all the bathymetric data into a freely available map through GEBCO. Now, the funding for this is not paying for the collection of data. It's really paying for this facilitation of the collection of data. But even that has been a tremendous help. It's structured with a project team that represents 4 regional centers for the North Pacific and the Arctic, the Atlantic and Indian Ocean. There's a global center in the UK, a Southern Ocean. That's at Alfred Wegener Institute. Pacific and Southwest is at NIWA in New Zealand. Atlantic and Indian Ocean at Lamont, and North Pacific and Arctic at our lab and at the University of Stockholm. And these groups have been focusing on their regions over the last few years, trying to shake the trees for what data exists, as well as accumulating new data. And if we look at the progress from 2018, where we started with 6.9%, by 2019 we had 15%, and 2020, the last production of the GEBCO grid, 19.7%. So we're up to almost 20% of the ocean covered. That's been a great increase in just a few years. But the scary part is that that's mostly been finding existing data that people either had in a drawer, weren't too comfortable releasing. We're getting people to be much more comfortable releasing it. And now we're really running out of that, to be honest. And now we face the real challenge of how do we collect the rest of that data. And so we need to take a look at what that effort is. It's a problem that scales by depth because the multibeams get wider and wider as we get by depth. We lose resolution, but there's no changing that physics. So if we look at, again, a back of the envelope calculation of what it would take using current technology, which means an oceanographic vessel with a deep water multibeam on it, and looking only, this is important, at 200 meters or deeper. That represents 94% of the world ocean, and that's because the shallow water kills you in terms of time. We say, let's not throw the baby out with the bathwater. Let's see if we can get 94% of the ocean done, and then we'll leave it to local entities to focus on the shallow part. We can have a conservative estimate of 3.5 times water depth and a ship of 7 knots, or a less conservative 4 times water depth, 10 knot surveying. We'll change the number of days it would take to do that with this distribution of depth. Guess at an average cost of a oceanographic research vessel at $45,000 a day for a deep sea vessel, and we come up with an estimate of $3 to $5 billion to map the world ocean. Who's going to spend that kind of money to map the ocean? Well, we spend that kind of money quite often to map other planets. Mars is mapped completely at 20-meter pixel resolution. A lot of it at 1 meter resolution, and a typical Mars mission costs between $2 and $3 billion. And I don't want to take anything away from a Mars mission. It's fantastic that we do it, but don't you think we owe it to our own planet to map it and understand what's going on there at the same time? Of course, for Earth, what we have is 81% of the ocean basins would look like that in terms of our mapping. We have the capability with surface ships to do the rest. I told you, for $3 to $5 billion. And we have the capability to do the 1 million resolution too, 1 meter resolution too, but that's going to be with autonomous underwater vehicles because we have to get close to the bottom, and that you can scale that 3 to 5 billion up by several orders of magnitude to do that. So let's take a look at a way that we might try to reduce that cost. If we look at our current technology and look at the cost of a typical oceanographic research vessel, we have a distribution of something like that. Crew costs about 30%, fuel costs 35%, consumables about 3%, so on. If we can remove the crew costs, we have reduced a large component, and it'll reduce many of these other costs. So if we thought of something like an autonomous vessel, say an autonomous barge, which is a wonderful form factor for a multi-beam system, we can start addressing certainly some of the crew costs and some of the duration issues too, because you don't have to, on a barge, you can carry a lot of fuel, you don't have to come back to port and so on. And maybe even some larger weather windows too. But what if we can reduce more than just the crew costs? What if we really can reduce the fuel costs and consumables? And we've seen a wonderful innovation with sail drones, now sail-powered vehicles, autonomous vehicles. They've been out there for 6 months, 7 months at a time. These vessels are about seven meters long or so. Wouldn't it be neat if we can do something like that? Because if we can replace the engine with a sail, we would now reduce the fuel costs, the consumables. We'd have other costs associated too, but tremendous potential for reducing cost. So I said it's a 7 meter. You can't fit a deep water mapping system on a 7 meter vessel. So what we've been doing is working with Saildrone, and Saildrone has taken a great leap forward. And there is now a 22 meter vessel, 72-foot vessel that has a deep water multibeam on it. Just to give you an idea of the scale of this here, you can see that's the gondola with the multibeam system on it. And so now we've entered into the world of deep water mapping with a vessel that potentially, an autonomous vessel that can potentially reduce the cost quite a bit. It doesn't just have a deep water multibeam, it has a shallow water multibeam, a full suite of EK, fishery sonars, ADCP, a full suite of environmental sensors, and a Mabari eDNA sampler on board too. Now we've been undergoing sea trials of this vessel for the last few months. Here it is in San Francisco, where Saildrone is, Alameda, going out into the bay to do its sea trials. We've been working diligently with it. They have a wonderful mission portal where, again, you can remotely pilot the vehicle, get the situational awareness you need. We've been collecting multibeam data remotely, which has been a challenge, processing it remotely, running through a series of initial patch tests and trials, and collecting some spectacular data. We're all ready to put it to its first test. We have a new tool that we've developed also that lets us plan a route. We hope to take its first trip, funded in part by the Nippon Foundation, from San Francisco to Hawaii, hopefully next week. This tool that we've developed lets you now plan a track, look at the swath coverage you'll get on that, but compare it to existing data and move it so that you can optimize new ground coverage all the time. And so we think we're ready. Hopefully that'll head off to Hawaii. I said next week, we'll see. And let me use that as a way to end. It looks like it's a sunset, but this is actually a sunrise, because I think it's much more fitting for this field that we're really not at the end of anything. We're really just at the beginning. So let me end there, and thank you all for your patience. And happy to answer questions now, or just hang out with the students later. But again, I wish it was at Cage Brewing. So I'll stop sharing my screen unless I need to bring it back and turn it back over to you. And Steve, Sarah, I don't know who's going to take over now.
I'll do that if you want, Sarah. Thank you very much, Larry, for a great seminar presentation. Like to open it up for questions for people who haven't used Teams before. There's a little face with a hand. If you go there, and you can pop the hand up. I have a question to ask you. You talked about mapping the 94%. Those of us who live on the 6%, that's obviously a huge problem in terms of the efficiency of mapping. I'll say, and I know you're aware that the state of Florida just passed an enormous initiative to map its coastal waters. $100 million was allocated by the legislature. How are we going to do it?
Yeah, it's a great question. It is difficult. I think we're seeing lots of important advances in terms of laser bathymetry in some areas, LiDAR. We have approaches with not satellite-derived bathymetry from altimetry, but satellite bathymetry from imagery that's coming of age too. And I think we can be very careful with water clarity. Those are all constrained by water clarity, but if we're careful with the water clarity issues, careful with timing in terms of tide, we can optimize that really, really difficult part, which is 0 to 10, 0 to 20 meters. Once we get beyond that, then I think we're in an area where things get a little easier. The efficiency gets better. Sonar systems are quite capable in those areas, and then we start thinking about force multipliers with smaller vessels like smaller sail drones or other autonomous vessels that really can act as a force multiplier. So I think it's the possibility is there. Certainly, it's just going to take a lot of concerted effort. Maybe we'll use Florida as the perfect test case. There's a lot of work been done in California too, and I think Fugro did a tremendous job of showing what could be done in California.
I noticed that Ed Sade is on our list of attendees today, and
Oh,
I wonder if
I didn't know that. So
I think he's still
I
here. I'm
shouldn't have
not
said
sure.
that.
And well, he may have jumped off actually. I was just going to ask him to comment, but he may have jumped off. But another colleague is on that I actually wanted to acknowledge and maybe have her maybe weigh in. Dr. Dawn Wright from Esri is on our list as well. And I wanted to congratulate Dawn on her recent election to the National Academy. And I'm wondering, Dawn, if you would like to pop up and maybe comment or ask a few, maybe make a few salient comments to Larry.
I'm just honored that Don joined in. That's really wonderful. Thank you.
I'm honored as well, Steve. That's very, very kind of you. And Larry, you are the master. It was a fantastic talk, and I loved how you ended the talk with the beginning. And I think for those of us at Esri, we are just doing everything that we can to support the data side of things. And what was really heartening for me was to hear about the sail drone surveyor. I'm not sure how many of us in the community were aware of this recent development, and that's, to me, that's a real game changer. So we will be looking very closely at the trials in Hawaii, which I imagine will be on Sail Drone's website. So that's fantastic, and thank you for a terrific talk.
Thank you, Don. Again, it's an honor coming from you. So.
We may want to be talking to you, Don, about some sort of portal for all the Florida mapping things that are ongoing. It's pretty exciting to try to put a picture like that together.
Yes, because I think so many of us now are investing in the effort toward open data and getting the data processed and open and out to the public as quickly as possible. One of the things that we are facing right now in terms of land cover, global land cover, is that there's great need for that as well. And there are many organizations that are working on 10-meter global land cover. And we're having discussions now about getting that out sooner rather than later, and walking that fine balance between putting an embargo on data so that you can publish on it, which is of course, the old traditional way of doing things, to thinking of ways where there might be a co-publishing arrangement, or even, this is controversial, but foregoing that publishing, or trusting the rest of the community to give you that courtesy, but getting that data out as quickly as possible, because we're running out of time towards Seabed, towards 2030. When the year 2030 comes up, I just think Seabed 2030, but there are many other 2030s out there. But at any rate, Steve, we would absolutely love to work with you on open data hubs. That's one of our big initiatives right now, including for bathymetry, and we're of course working with Seabed 2030. Thanks.
And another aspect of that, I agree with everything Don said, is the whole concept of DOIs, which I know Don has been very, very involved with, and I think that's helping very much. And I think even NSF is starting to recognize that a measure of productivity is also the provision of data. It's not just the publication in the end. It's a very real contribution, is the provision of data. And when that mindset starts being changed, we're all going to be in a much better place.
Indeed. Any other questions for both of our guests today?
Dave Nahr, my friend Dave Nahr. Hi, Dave.
Hi, Don. Good to see you. There's actually a question in the chat I thought I'd share with you, Larry, since you've answered this question many times before, but I think the audience would like to hear it again. Regarding the assessment of multibeam interaction with marine mammals and whales and the frequency dependence and so forth.
Yeah, so it's a terribly important question. I think generally in the regulatory world, the consideration is that at frequencies above 200 kilohertz, so most of the shallow water multibeams that's above the sensitive hearing range of most of the marine mammals. So there's less concern about that. But the lower frequency multibeams, there certainly is concern because 12, 30 kilohertz is certainly within the hearing range of marine mammals. We've done a lot of modeling. Our colleague Xavier Lerton in France has done some very serious modeling. What you need to think about in terms of multibeams in marine mammals is how short the pulse is, milliseconds, and how very, very narrow and tight the beam is. We know for a fact that the Navy mid-range sonars, which are in the same frequency range as these things, have an impact. But those mid-range sonars will have a tone that goes on for almost a second sometimes. And these are very short. So we've never really felt, to be honest, and I have some anecdotal indications in terms of experiments we've done with tagged marine mammals that was done with fisheries and running a multi-beam and seeing no indication of any impact. But over the last 3 years, we've actually taken this to heart in terms of putting it to a test. And so we were able to get access to the Navy hydrophone range off Southern California and the one in Autech. And we're able to, we were out there for the purpose of understanding the true radiation pattern, measuring the radiation pattern of the multibeam in a very sophisticated hydrophone array. And we were able to do that quite clearly. So we now don't have to model it. We really have it measured. But at the same time, in both of those areas, particularly the SCORE area, the Southern California area, there are resident population of Cuvier whales, very sensitive marine mammal. And those marine mammals vocalize every time they feed. And so the Navy hydrophones can track their behavior. They've been tracking them for years, and that was actually the evidence that the Navy sonars had a great impact. When the Navy sonars went off in those ranges, those beaked whales would really change their feeding behavior, and many of them actually left the range for a few days. And so we actually went through the exact same set of analyses we had a controlled period before the multibeam got there, a controlled period of the vessel without the multibeam, a period of the vessel in the multibeam, and a period after. And out of 8 parameters that measure impact on feeding behavior over we repeated the experiment 2 years in a row. So there was 16 different indications of only one of them indicated at all any impact. And the impact was an increase in feeding behavior, tiny, almost statistically, and it was in the opposite direction. And it was after that they increase of feeding behavior after the sonar, and it very much might have been a prey thing that prey moved in. And so I think there are several papers have now come out, one in JASA and one else, another one is coming out in an issue. So I think we're for the first time having not just anecdotal but real fact-based evidence that multibeams appear not to have an impact, at least on the feeding behavior. And that's been the metric that's been used for impact. Steve, you're closer to that than I am.
Well, I'm not going to comment on that. That's sort of outside my range as well. There's another question in the chat from Frank Mueller-Carger. And Frank Mueller-Carger has been working on the Marine Life 2030 MBON initiative, and he wanted to see if there's any possible linkage between Seabed 2030 and Marine Life 2030, and whether or not, in the process of collecting, the geophysical data, that we could actually collect more biological data.
Yeah, so that's a great question, Frank. And it's something throughout the evolution, at least of the NOMIC strategy, the U.S. Strategy, that we've tried to encourage, and we try to do it ourselves all the time, no matter where we are, that at least as we are collecting the bathymetric data, there's no reason why the water column and the multibeam can't be collected. And if we can, without interfering with each other, as we do that through synchronizing, uh, be running the fisheries sonars too, which are much more calibrated and really start giving us a much better picture of what the distribution of at least scattering layers are. And the question then becomes how much ground truth. We're going to be going out with an OER funded project with the Mesabot and the EKs and the autonomous vehicles to see if we can kind of establish a protocol for understanding what's coming back from the fishery sonars and the multibeam sonars, the bathymetric sonars, ground truth by Mesabot, to see if we can, wean ourselves from the ground truthing and be able to interpret the midwater stuff. So yeah, Frank, that's something we might want to talk about a little more. I think that's great.
It's a tremendous opportunity to get full water column, information for sure.
Boy, you talk about data rates. Wow.
Any other questions for Larry? Don't be shy.
I don't see any hands up or any more questions in the chat.
Well, maybe Larry, you want to have a little infomercial for the National Academy's Revell lecture?
Sure. So tonight at I think it's 5:30, the annual Revell lecture, which is a very prestigious lecture. Don gave one a couple of years ago. Is going to happen. It's going to be a little different tonight, which is it's kind of exciting. So our focus tonight is going to be early career ocean scientists. So we have 2 lecturers who are early career scientists, and then we'll have a panel of early career scientists, and the focus will be on early career scientists contributing to the decade of ocean science for sustainable development. So I think it'll be I'll miss. Yeah. Oh, somebody has actually put it in here. Yeah, the next wave. Yeah. I don't know how to read. I keep seeing little things flash up, but I can't read them. They're just the first line. Sarah, did you put that up? So could you read what that says? Because that's the official title.
It's it's the next wave, a generational shift in ocean sustainability is the title.
Thank you, Sarah. Yeah. So please join in. The big event will be for 5 years. I've had to introduce it, and I only own one suit, and so my wife was always very upset that every year I came with the same suit, but I also explained it was the only time I ever wore it, so it was no big deal. But tonight I won't have to wear a suit. I refuse to put a suit on in my house.
Any other comments or questions for Larry? If not, there's Matt Homar.
Hi, Matt.
Hey, Larry, how are you?
I'm okay.
That's good to hear. I know you've mentioned this in the past, but perhaps not in front of this audience. If you could riff a little bit on how initiatives like NOMEC and Seabed 2030 are not only a technological and logistical challenge, but there's a real need for sort of political and organizational mechanisms to be in place to actually make it happen and make it happen seamlessly, so it doesn't end up being a sort of random patchwork of postage stamps.
Yeah, that's a great comment, Matt, and it's very, very true. And this is the beauty of the Nippon Foundation's contribution, because that's what they've actually are paying for, is an organizational structure that's trying to, I'm not saying succeeding yet, but trying to ride herd on just that issue, to make sure it's not just a patchwork of random data sets, but there's a common thread in terms of processing, quality control, a uniform product that comes out. So there's that side of the non-scientific aspect, and that's a critical one. And this morning there were several hours of the GEBCO guiding committee meetings where they're discussing that same thing because it's part of their project. But there's also the other aspect of it, and here's where I have to admit I've been really pleasantly surprised. You saw that those huge increases go from 6 to 20%, and most of that just through data discovery. And people are starting to buy in. And it's a lot of those are political decisions, government decisions that will we release our data. Norway or Finland just a couple of days ago released a huge patch of data, seeing that it's for the common good. And when the momentum starts growing, I think we might be able to keep those high numbers just through, again, release of data sets that have been held in vaults somewhere. There's always strategic issues with that, that governments have to worry about. But we're not asking for the data. We're happy to take it at the full resolution, but it's not necessary. There are prescribed resolutions that Seabed 20 asked for, and there's nothing higher resolution than 100 meter. So a lot of the national security issues are taken away when you have data at that level of resolution.
Other questions? David?
It's just a real quick follow-up on the GEBCO 2030. The remaining portion of the ocean's 200 meters to the beach. Of course, it's going to take a great deal more time. Has anyone actually gone and done an estimate on how much longer it would take in an ideal world where everybody was cooperating?
Yeah, I think it's a hard thing to do because we can do the estimate assuming that nothing is mapped. We can do the estimate with what data is now available, but we know, and that's the area that there's a lot more data that's already been collected. And it's so difficult and expensive to collect that it would be a real sin to do it again. So I think this is again where GEBCO's connection to the International Hydrographic Organization, which is connected to a much broader UN-based network, and Seabed 2030 as an international program may start elevating that to national hydrographic offices who are going to say we will make the contribution, we will contribute data. I told you Finland yesterday, or a couple of months ago Ecuador came in and said that they'll contribute their data. And so it's starting. It's slow. It's starting, but sometimes you just try to embarrass people into doing it. So. Yeah. But I'll tell you off just totally rough estimate is I estimated, assuming nothing had been mapped, that the 0 to 200 would be an order of magnitude more than the. And so we're talking $30 to $50 billion, but a lot of that's been spent already, and that's what we need to. And that did involve, and that was pure sonar too. That did involve all we can do with LiDAR and satellite derived bathymetry.
So did you mean 20 more years for shallow water if everything was working properly, if there was no data available?
I didn't do a time. I did a time. I did it in ship days basically. So it could be 1,000 ships and take a year, or the deep water is 200 ship on the order of 200 ship years. So full years. So again, we can do that 1 year with 200 ships working 365 days, but that's again why we looked at something like if you can get 10 sail drone surveyors out there working 24/7. It's quite the deep water problem is quite manageable.
Thank you.
So Larry, I have another question for you, and that's given the inventory, what might there be held by the world's military that could be actually contributed? I'm reading a great book right now called Science on a Mission. I don't know if it's a history of physical oceanography, and it talked a lot about Cold War, information. And I wonder to what extent there might be holdings there that could really advance this.
Yeah, I think it's certainly possible, and I think early on, and when I say early on, this is 20, 30 years ago when there was another Admiral Gaffney led an effort called GOMAP, which was, and I think the approach at that point was if the academic community was going to do it, just do it. Don't worry about what the military was holding. It was just going to be too difficult an effort. and it was probably too piecemeal. Some cases that would be the approach. Other places, I think the answer might be that with careful introspection and careful discussion, many of the folks who are holding data for military purposes may be comfortable releasing it at some level of resolution.
Right.
And so that's where I'm hoping we'll make gains of one by one. With each government, you say, well, you comfortable with 100 meters? Well, no, are you comfortable with 200 meters? At some level, it really stops being tactical and even strategic. And so I think that's going to have to be the approach. But I think without question, there are holdings. There are holdings that are not just military. There are a number of the nations that collected data for Law of the Sea for their extended continental shelf have data sets that have not yet released those, and that may or may not have anything to do with military concerns. It's a different concern, and I don't think it's a well-founded one, but we need to work on those arguments.
Okay, I wanted to thank you again, Larry, for all of that and for answering all these questions. I wanted to put out our own infomercial for June 23rd. Rich Edwing will be giving the monthly seminar. Rich Edwing from the co-ops program at NOAA. Very interesting set of information that they generate, and so we're all looking forward to that. Anything else we need to talk about, Sarah?
Nope, now is just the time for the students, if there are any on, who would like to stay behind and have some more one-on-one time with Larry. Otherwise, yeah, no, I'm just going to drop the next seminar in the chat here, the webpage for Rich. So yeah, he's got his abstract up there already.
Perfect.
Thank you, Larry.
Well, thank you all. It's been fun.
All right. Yeah, so students stay behind. And Larry, if no one stays behind, you get an extra 45 minutes all to yourself today. So.
Oh,
He can put on his suit.
That's
yeah,
right.
I could practice.
Very good. I have to bop off to another meeting, Larry. Thank you so
Steve,
much.
It was great
Thanks
to see
again.
you, Matt. Great to see you.
I need to talk to you about a few things as well, but I'll do that.
You know where to find me, unfortunately.
Cool. Thanks again.
Looks like we've still got a few students here with us. So let's see. See Alex.
Alex, how are you?
Good. How are you doing? Great
Okay.
talk.
Oh, thank you.
So students, if anyone has a question for Larry, go for it. There's not so many people here that I think will be tripping over anybody. So, or if you just stayed behind to look at Larry, that's okay too.
Well, believe me, that's not okay.
I'll start with one question. You briefly mentioned when talking about shallow waters that it would be, very expensive, so you wouldn't want to map areas multiple times. But at the same time, those areas are probably the most dynamic and the ones changing. So when you talk about satellite mapping, we're getting new satellite images every day. So how often do you think we're going to need to update these maps? If we successfully map by 2030, is there going to be a Seabed 2040 to remap everything, or where are we going after there?
Yeah, that's a great question. You're absolutely right. I mean, certainly, particularly in the shallow water, there are areas that are very dynamic and need to be repeatedly mapped, even for safety and navigation purposes. And NOAA does have internally in NOAA, they have an approach that helps them predict where they need to map their prioritization process, and they've started to include sediment transport models and things like that into that to try to have an idea. They right now there's some name for it, and I forgot what that name is. But if an area is a bedrock area, they'll call it a fairly stable area. They'll make some general assumptions, but I think the long-term goal is to really get a hydrodynamic and sediment transport model in. And so that'll hopefully be a guide. I guess people are always asking this, and it's absolutely right. To me, changes are some of the most most important and interesting things. But I guess I'm still thinking let's get one done first, and then we can worry about the changes.
Cool. Thank you.
Anyone else? Edmund, nothing on fish water column.
Oh, well, Larry, fantastic talk.
Hi, Eddie, how are you?
How you doing? Just an amazing number of topics covered. Just curious, really just curious on the COMIT front. Are we going to see you down this way a bit more?
I hope so. I hope so. I actually took my first plane ride Friday, and that was for Rick's funeral. It was probably a little earlier than I wanted to. But no, I'm hoping that we'll evolve to the real world, and then I'm hoping that our collaborations will be such between the two centers that we're already on the crowdsourced bathymetry. I think there's been a lot of good stuff going on, and so I'm hoping that we'll have regular exchanges in that sense.
Excellent. And on that note, I might just follow up with the one schematic you had. It looked like the EK transducer array was on a swivel with some of the work you were doing. Are you doing that from is that a hull mount or is that a special pole mount?
Yeah, it's a pole. It's just a pole. Yeah, so it's just a little rig that we built. And to be honest, right now the swiveling is done by basically running it back and forth, moving the vessel, because we can track the angle. So we're manually doing that tilting. But Kongsberg is building one with a mechanical. Kongsberg actually wants to make a product out of it that'll have a mechanical control on the tilt.
Very interesting. Very interesting. Well, again, thanks. Great talk. Great to see you.
Right.
Larry, I have a quick question. This just popped in my head, so it's a little random. So with technology advancing as quickly as it is, a lot of us have things on the shelves that are now like essentially obsolete. And it's too bad because they're still functional. I mean, do you see some of these, I guess, quote unquote, outdated technologies as having any value in what Seabed 2030 is trying to do? And I'm wondering that from a context of, there's a lot of governments around the world that cannot afford these really fancy cutting edge technologies, nor have the people to use them. So I'm curious if there's ever been talk of equipment transfer.
I've heard discussion about that, but the UN Decade might be a great place to bring this up again. Years ago, I heard. Well, I guess it was when there was the big earthquake in Chile. I think it was somewhere there was a terrible earthquake, and one of the oceanographic centers was really hard hit, and so there was kind of a collection taken up around the world for equipment to restock them for, and again, it might not have been the most new, but it gave them something to start with. To be honest, we got to be very careful these days about even offering such things, because it's often taken the wrong way, that that the developing countries don't want to feel like they're charity cases, that they want to. But let me bring this up at the next decade meeting to see if we might want to think about that as a national effort to kind of create a stock of underused surplus oceanographic equipment that can be part of our contribution to the decade.
Great, thank you. All right, anybody else? I'm sure, like I said, Larry's been going since early this morning, so I'm sure you won't mind the extra break.
No, I certainly won't, but it's been fun. I do wish we could have gone to the pub though, and that makes it much more fun. So.
Mm-hmm.
Although today
we'll just have to hit it double hard next time.
Yeah.
Next time around, so.
That's right. It's I owe you. All
right.
All right, well, guys. Thank you. I never quite, as we were going along, I'd see things pop in. I guess there's no record of the chat, so I can't see the questions or things.
It looks like you got all the questions that were put in the chat. Yeah, it was the one about the marine life census and then the multi-beam interaction. Those were really the only two questions in the chat. Otherwise, what was popping up, I think, is that people had left the chat.
Okay. All right.
So yeah, looks like you got everything.
Okay. All right, guys. Thank you so much. Thank you for the invite. You got a good lineup of speakers coming. That'll be great.
Yeah, looking forward to it.
Okay. Put me on the list. Okay. Of